Welcome to the Digital Amateur Television Experimenters Night. This is VK7OTC, the club station of the Radio and Electronics Association of Southern Tasmania. Amateur radio is a worldwide hobby that has many different aspects. Digital television is just one of the many modes and areas that are covered. Maybe you're interested in becoming involved in the DATV Experimenters Night.
Going back a bit
You
now.
realise that you do not have to be a radio owner or need any ATV equipment to participate anywhere
Probably do
in
need
the
to do a
world.
bit of an update, really.
Well, that was pretty exciting, wasn't it?
That was very exciting, actually. That was very, very exciting. That was where I learnt, the ladder you took up there and you had it on the roof, and you had the oscillations as we got to a certain speed. As it was going through the rungs, I always remember it was just a fascinating bit of physics. And apparently it's a common occurrence on vehicles that have ladders on.
That's it.
They actually have special wind guard arrangements so that they don't get the oscillation.
You can also participate in the night by coming up to the Queen's Domain Club Rooms. Yes, the right top of the Queen's Domain and the heritage-listed Coast Wireless Station. You never know, we might get you in front of the camera or behind doing one of the many roles during the night. We get underway with our program on Wednesday night from 7:30pm local time.
I need something.
We'll see you soon. This is VK7 OTC.
Yeah, that's right. Anyway, okay. We are... Okay, this is VK7 OTC, the club station of the Radio and Electronics Association of Southern Tasmania with our DATV Experimenters Night, and I welcome Dr. Andrew Klekociuk. Andrew, welcome. And Rex, another contributor, another regular contributor, Rex Moncur VK7MO. So just before we get underway, I wish to acknowledge Tasmanian Aboriginal people as the traditional owners of this land and pay my respects to elders past, present and emerging, for they hold the memories, the knowledge and the culture and hopes of Aboriginal Tasmania. Now, I have Andrew and Rex in the studio for a few reasons. The very first one is we have a anniversary coming up. So
right.
Take us through the anniversary.
Yeah, 40 years ago, I was involved in a Space Shuttle mission, SpaceLab 2,
Yep.
and I just wanted to, just mention a few things about it in memory of the Ionospheric hole that was created over Tasmania.
Wow.
So that was the STS-51f mission. There were 10 STS-51 missions.
Okay.
I could spend probably about 10 minutes talking about the numbering scheme of the Space Shuttle missions, but this particular one occurred July, August 1985, and it was actually supposed to have been launched a little bit earlier, about 3 weeks earlier, but there was a gremlin in the shuttle system.
Okay.
19th Space Shuttle flight, 8th launch of Challenger, only made 2 more attempts
Yes.
before it was sadly destroyed.
Correct.
Second dedicated science mission, and the only in-flight abort where some sensors on two of the main engines failed, and there was a white knuckle moment when an engineer said, "Ignore the red line," and luckily they did, otherwise the shuttle would have been destroyed. So you can read about that, go and look that one up on the internet. But
That's a bit creepy.
scary stuff.
Absolutely.
But so this SpaceLab mission didn't actually have a laboratory inside the shuttle bay, but it had some instruments.
Okay.
There was an instrument pointing system which had an infrared telescope on it,
Okay.
making the first infrared observations from the shuttle. Found that the shuttle wasn't a good platform for infrared astronomy, and they did have some problems with the pointing system.
Is it because of the heat that was created by the shuttle itself?
And the low orbit, so it's the heat of the Earth as well affecting it.
Okay.
Plasma Diagnostics Package, a small sub-satellite which was waved around by the Canadian Canadarm and
yes.
actually free flew, and that was related to these OMS burns, or orbital manoeuvring system burns,
Okay.
which was the main thing that produced an ionospheric hole. Produced two ionospheric holes, one over Millstone Hill in the US and one over Tasmania. There were going to be more, but because the shuttle didn't get to the optimum height, they had to conserve fuel.
Okay.
Luckily, we got a burn in, and I'll say a little bit about that in a second.
So this is a burn of the main engine. Is this?
Yes, this is the manoeuvring system they used to change orbital height, basically, and they could move up and down a few tens of kilometres or even hundreds of kilometres. And of course, that was the system that was also used to boost the space station higher once they finally started building the space station.
A push, yes.
Yeah. Two other things of note: shuttle amateur radio experiment. So there've been, a number of, amateur contacts from space stations before that. But this was a dedicated experiment. I don't know if any folks from Tasmania are involved, but it'd be interesting to find out. And carbonated beverage dispenser evaluation, CBDE, which was testing whether they could taste the difference between Coke and Pepsi on orbit. They had this sort of carbonated beverage dispenser, and they were taste testing. So yeah, that's probably
serious
stuff.
If
you look at the wiki page on this, they actually say that was one of the highlights of the mission. Anyway, I disagree. So how do we get involved in this? Well, Tasmania has a long history in low-frequency radio astronomy. We've talked a little bit about this in the past, and Bill Ellis and others had actually made radio maps at low frequencies using the low ionospheric critical frequency in Tasmania. Grote Reba was another important person in that. Radio maps at 2.3 and 4.7 megahertz, which had not been achieved anywhere else. In fact, the low-frequency radio sky was a bit of a mystery until Tasmania got involved. Michael Mendello in the US had actually proposed an experiment, early on in the shuttle's program to build on some work that had been done. In 1973, they noticed when the Skylab space station was launched, the Saturn V burnt its way up to about 300 kilometres and created this massive hole in the ionosphere, which was noticed in a number of ways. And then there were some other experiments that followed on from that. The High Energy Astrophysical Observatory, there was a dedicated mission to that. Mendello proposed something for the Space Shuttle. And, there was a Star Wars connection, because by creating these ionospheric holes, it was thought that you could send your particle beam weapon through to destroy satellites more efficiently. You get rid of all the ionisation which would attach to those particles being blasted through the atmosphere. So, we won't say too much about that.
This was the...
Why did they call him Graham or Bill?
Well, this is one of those things. This is another mystery. He was Graham, Reed, Anthony Ellis, and they called him Bill. So,
right. Okay.
Yeah. Anyway, that's another story. You can actually probably look that one up on the internet.
Yes.
Anyway, Michael Mendello is still with us. Bill Ellis passed away. He was in his late 80s. Not that many years ago. And like Mendello's now still going on, and actually doing some interesting stuff with all sorts of ionospheric studies, mercury, plasma tails, all sorts of other things like that. Anyway, coming back to these ionospheric holes. So as rockets burn through the ionosphere, they create positive ions, and electrons like to combine with those, and then in the process they give off this characteristic 630 nanometer emission. And it's actually one from related to a SpaceX launch in 2023, and they see these things from the US occasionally. You've got to have a dark sky, but basically where there's this recombination happening, you get this emission, and that was actually one of the things we were looking to study in Hobart, but unfortunately it was all very cloudy. I was involved in a CCD camera that we had through the surveying school of surveying. Tony Sprent spent a bit of time with one of the early CCDs trying to actually increase the exposure length, and we put a filter in front of it and actually were able to see air glow, but it was completely cloudy over Tasmania, and I was involved in that experiment. And also La Trobe Uni had a camera as well.
Okay. So Andrew, that's you refer to that as air glow. That's not an aurora. We're not looking at an aurora there.
No, it's an air glow process. So it's basically a chemical process inside the atmosphere, as opposed to being energised by energetic particles spiralling into the atmosphere. So cameras now are great for these sorts of things, and they see them in the US, and maybe we can see some here in Tasmania. Anyway, so very quickly on some points about the ionosphere. So on the left there we've got the nighttime ionosphere, the F layer at about sort of 250 kilometres, and that's kind of the key one, of course, for radio amateurs. And that's where this ionospheric hole was created. So the idea was to reduce the electron density in the F layer. Good thing about Tasmania, in the middle plot there, we're near this mid-latitude trough. So the ionospheric density, or the critical frequency, at night, in the right-hand side of that plot there, is at a minimum around about our latitude, actually somewhat slightly further south, and that's the ionospheric winds blowing electrons away from these latitudes. The daytime hemisphere, it's quite different. And then the top right-hand plot there, that's the FOF2 ionospheric critical frequency. Again, quite low at this time of year, so that plot's for June. It's the lowest on the planet, essentially, in our latitude range, and that's a combination of this plasma trough effect. Solar activity in 1985 was at a minimum. At the moment, we're sort of just past the maximum. Again, that also contributes to these low ionospheric frequencies. So the idea is that if the frequency is really low, you can see the galactic radiation coming through the ionosphere.
Okay.
So back at Lanherne, out at near the runway out there are a number of different radio telescopes. You can look at papers by Martin George that describes the history of this in quite a lot of detail, quite fascinating history.
Who's still writing for the Mercury,
still
radio
writes for
astronomy,
the
and etc.
That's right, So you can look up, his papers are publicly accessible, talks about all these different arrays. There was a
is that at the airport?
Yes, that's right. It's all been bulldozed now, and pine trees planted around it. But there are a number of different things out there. There was this 1.6 megahertz array, and Bill Ellis put in another array, essentially, that was covering a wider range of frequencies. These things are quite big. They're half wavelength dipoles, and phased to have a beam overhead, about 25-degree beam, so fairly broad. But it'd be interesting to try these sorts of experiments these days. So you think you could do, you still need, dipoles, but you could have phasing arrays that point the beam, and that would be
might have more noise.
Yes, you'd have more noise. That's so much more noise, that's right. Don't tell me about it. Anyway, so in the middle plot there we've got a map of Tasmania. There was a burn track. It was a fairly quick burn over Tasmania. The shuttle was basically changing its orbital height slightly, and some folks in Melbourne were monitoring the sub-ionospheric point. I went up to Avoca with that camera system, but I also took with me my shortwave radio, my national Panasonic shortwave radio, with a newfangled LED display and phase lock loops and all sorts of other fancy things,
modern,
and a tape recorder, and I recorded the audio output of a 1.9 megahertz beacon that Ellis was using to look at long delay echoes, and I mentioned those in the talk I gave recently. So anyway, I took that up there, and we actually got some results, and there are some papers you can look up. Unfortunately, all of these are behind paywalls.
Oh my goodness.
But one day, hopefully, all research will be free. Yeah, that's my utopian hope. But if anybody's interested in those papers, they can contact me and I can send them to them. Anyway, so what happened was that the Space Shuttle did its burn. In the left-hand plot there, we've got the FOF2, the Ionospheric critical frequency measured by Ionosons in Hobart and one in Melbourne. And these are the days when folks hand drew graphs
Plots,
with
yes.
rotating pens.
Okay.
But I've gone back and had a look at the data. You can actually get the digital data online at hourly resolution for this time, and I've verified yes that it's as shown, which is good.
Okay.
And so the Ionospheric critical frequency dropped suddenly and then fell away, as it kind of generally did at this time of year and solar cycle, but it did depress it more than usual.
Okay.
And that enabled...
So you were scanning the frequencies to see this?
This is with our Ionoson.
Yeah.
So it's doing I think this was set to run every 5 minutes, or actually around this time it was every 1 minute, because I think, 2 minutes actually, because I think the Ionoson took about 1.5 minutes to scan.
Okay.
Yeah, so it was it was running flat out for this. So the Ionospheric critical frequency dropped. Up at Avoca, I was with my 1.9 megahertz receiving system there, and I actually produced a digital plot.
Okay.
And I guess it's kind of the forerunner of what folks do all the time now with SpectrumLab and the works. But I actually had to play this tape back through a D to A and digitize it and do all that sort of stuff. And I saw the beacon fading away after a period, and I've gone back and had a look at the circumstances. The angle, about 75 degree elevation, calculate your critical frequency for that path, and given the change in FOF2, it tallies with this decrease after a period.
Okay.
Now back in Hobart, the bottom plot shows the galactic radiation coming through at different frequencies, and as I mentioned, some work had been done at high frequencies, but here for the first time they've actually seen signal at below 2 megahertz essentially.
Yep.
And that was kind of one of the key things.
And quite a marked drop.
Yeah, that's right. A marked drop in the critical frequency, and then allowing the radiation to come through. That's sort of showing you that things happened at the same time. Anyway, so radio sky at 1.6 megahertz. Really hasn't been much done since then, because earthbound observers are limited by the ionosphere. Chinese are very interested in doing this from the moon. At these low frequencies, the plasma in the interstellar medium acts like a fog, and radio waves get scattered off it.
Okay.
So you'd actually have a hard time seeing stuff even within our galaxy. So there's the plot on the left produced by Bill Ellis and Mike Mendello, and they observed over a few hours as we saw the ionospheric critical frequency dropped, and produced this map of a part of the sky.
Is this in Kelvin or something?
Yes, these are in brightness temperatures in Kelvin, so they're millions of degrees Kelvin.
Millions of degrees.
Yes, so there's synchrotron radiation happening essentially. So it's radio electrons spiraling in the galactic magnetic field, producing this emission. And then on the right, I'm showing a map at 406 megahertz, which was made a few years later, or around that time, kind of. And what you're seeing in the Ellis and Mendello map is the galactic center. These are plotted in galactic longitude, and the loops that you can see in the right-hand image, that they're blown out by supernova events in fairly recent times, in the last few million years, and there's some hint of seeing those in the Ellis map. So some interesting stuff coming out of that. So eventually we'll get maps like this. There are some satellites. There was a satellite called the Radio Astronomy Explorer, RAE.
Okay.
Coincidentally, Graham Reed Anthony Ellis, GRAE, just a coincidence.
Just a coincidence.
Anyway, around that time, but the last there's been a big gap in low frequency radio satellite measurements. There was a satellite launched a few years ago. It had some problems. There's a heroic paper that I've seen where they literally analyse a few minutes of data before it went kaput. And they did actually see the radio sky again at these sort of frequencies, or actually could actually see HF communications and various other things. Anyway,
Okay.
go and look that one up. Yeah. And then finally, a bit of a challenge for amateurs here. So, SpaceX rockets, the second stage burns, the deorbit burns happen near Tasmania. So here's some pictures of some clouds thrown out by these rockets. And I actually picked up one on my all-sky camera. That's the one on the left, which happened over the big spiral cloud over New Zealand. There's one in the UK on the top right. And then just recently, an amateur spotted this interesting cloud over the goldfields in Western Australia, which is from a Chinese rocket. So there are rockets doing burns in the ionosphere. This is the thing. And
It's 3 days ago.
yeah, that's right. It's pretty recent, so I'm on the ball.
No, fantastic.
Yeah, some folks said, "Oh, yeah, it's SpaceX," but I said, "I reckon that's Chinese." So anyway, we tracked that down. But yeah, the challenge for amateurs is that yes, there are these effects happening in the ionosphere. They could be ionospheric holes, so there'll be anytime you do a burn, you'll deplete the ionosphere. But these things are throwing out clouds of ice that are being eliminated here by the sun,
Okay.
and the ice will scavenge the electrons as well, and they might actually be like a sporadic E layer. So, you know, folks try maybe some FT8 or something like that.
So what height are we talking about here? Which layer?
Yeah, we're talking about the F layer here,
Okay.
basically. So it's going to be different to your sporadic E, which is lower down.
Okay.
Problem could be your E layer might be blanketing.
Blocking it.
Yeah, blocking it too. Although you might get.
But this is longer distance stuff. This is.
Yeah.
Yeah.
So these SpaceX burns happen near Tasmania because there's a ground station that controls the satellites, and they like to send a signal from here.
Okay.
It's a bit hit and miss, like if you knew when to look, that'd be great. But SpaceX are a bit secretive. But generally, once there's a launch, you've got sort of about an hour, depending on where it's coming from. If it's coming from the US East Coast, it could be an hour. It could be a bit less if it's coming from the West Coast, depending on inclination.
Yeah.
Although if it's high inclination, it might take a few orbits to come around to us.
Okay.
Don't know. A bit of a challenge, perhaps, if people are interested. If anybody's interested, they can contact me and we can talk about it a bit more. That's it.
Wow. That is off the show.
So it's still relevant today.
Oh, well and truly.
Mm.
And in fact, even more relevant because of the number of flights.
Yeah, that's right.
That are occurring now. It's now just going back to those pictures. Is the different shapes because at that F layer there are obviously different things going on and different flows of that particular layer. Because the spiral one in New Zealand, that's fascinating.
Yeah, it's a rocket sort of out of control, essentially.
Okay.
It's just got its vectors,
So that'd be one of the stages coming to Earth, back down to Earth or something like that.
Second stage, deorbit burn, not along the direction of travel, it's spinning sideways, essentially.
Okay. And the Chinese one, I assume, it's going in that direction.
Yes, that's right, yes. That's I think it might be a third stage burn to get to a higher orbit.
Yeah,
that kind of thing.
No, because that makes more sense. Okay.
We are in the firing line for Russian rockets too, and I've seen a re-entry over Tasmania from a Russian second stage.
Okay.
So there are things like that happening. Not sure I suppose there is spent fuel in that would cause ionospheric effects. But
okay.
I've had a little bit of a look at Whisper logs to see if I can match up anything with these. No, I haven't found it yet. You'd have to be very lucky. But look, there's a challenge there if people want to explore these things. I don't think there's any reports yet of this sort of burns.
But by the
creating-
sound of it, there's plenty of the optical phenomenon
Yeah.
that is being captured.
Yeah,
It's-
that's right. Yes, nighttime, and you'd want to do this at night when, the background ionosphere is weaker than the
Yep.
daytime. So,
Okay.
but if you might have the right path, New Zealand, Australia would be good for some of the SpaceX stuff.
Yep.
Yeah.
Okay. Now, I'm just taking a bit of a look. Hello to everyone online. We've got all our usual suspects, so including Ken. Ken's not in New Zealand; he's in Albury, and a range of Queensland VK3. Hello, Richard VK7 and Mark. VK7 as well. So any questions for Andrew, just drop them in the chat. That's probably the easiest thing, and we can grab him while he's in the studio. So that is outrageous.
Yep.
Andrew.
Yep.
That is
40 years ago. Yep.
phenomenal. Just phenomenal. Now I'm going to reach over here. Oh, there we go.
Might be useful to
We'll
swap.
just do the swapping.
We'll do the swap. While they're doing the swap, I'll just show off my T-shirt. The legalised recreational plutonium T-shirt. I'm a bit of an advocate for recreational plutonium these days. Probably good for rocket fuel, actually.
Okay.
Hello, Rex. Now,
Yeah, well, I originally came along to provide a bit more information on two articles that are in DUBUS. One which Andrew was involved in, line of sight DX propagation at 730 nanometers.
now this is the latest DUBUS.
Yes.
This is second quarter.
Yep.
2025, 75 years anniversary of the 2 metre sporadic E,
Yeah.
and there is a wonderful article in here by 3 people.
Yes.
So it's Rex and Andrew and Merv Millward, who is up at Georgetown? No,
Georgetown.
Georgetown.
Yes.
Cool.
Now, as well, there's another article in the VK section.
Okay.
Um,
At the back. Oh, there we go.
That, which is about
What we're going to talk about tonight.
what we're going to talk about. Well, we're going to talk about both of these articles, and that article was repeated in AR,
Oh, yes. Okay.
and it does actually attribute it to.
Oh, it does.
Yes.
See, I
But
didn't, I didn't read far enough, Rex.
Yes. But so we'll talk about that now, and if we have time, we'll go and talk about that one.
Fantastic.
Now, 13 centimetre lightning scatter. What happened was I got an email from Kevin for UH saying that
Keep going.
a couple of guys in Brisbane thought they had done some lightning scatter at 13 centimetres.
So you've started something, Rex.
Yeah, well, they tried it because Colin 4UV came down to our HamCon last year and listened to my talk about lightning scatter. And I said, well, send me the files, hoping they had saved them, and they had.
Excellent.
So
So we scroll down here.
we scroll down. Okay. Now they only got 3D codes,
Yep.
so they didn't complete a QSO, but at least they demonstrated that it is possible to get lightning scatter at higher frequencies than 1296.
2, 4, and 1 dB. That's
Oh, they're quite strong.
wow. Okay.
Yes.
Yeah.
Bear in mind, most lightning scatter's going to be in that sort of range
Okay.
because you're using MSK 144, which is a very
Short.
shortened mode,
Burst-
so you
burst
don't get
mode.
the benefit of integration like you can in
Yeah.
most of the digital modes.
So what you're seeing is that's how strong the signal is.
Yes.
That's not an integration thing. That's
No, that's
a
right.
real-
And you can see how strong it is by these little bursts there and that one there,
Yeah.
which was the 1 dB one. And this is one thing that intrigues me is there seems to be a tendency for lightning scatter to often occur as two bursts fairly close together. And these ones were only 0.1 of a second apart.
Okay. Any
Cloud,
thoughts?
ground, cloud, I guess.
Pardon?
Cloud to ground, then ground to cloud again. Returns.
I don't think any of them are ground. I think they're all cloud to cloud.
Okay.
But
Okay.
we can
Yep.
discuss that.
Okay.
So the next, I go down here, and what I did is I analysed this stronger one in Audacity,
Oh, okay.
and you can, and that's that from there to there is only 0.2 of a second. So
Okay.
this one's about 100 milliseconds, and then there's another weaker one. Another 100 milliseconds, but they both decoded separately.
Yeah. Okay. Okay. And that's 9 dB. That's that it decoded.
Sorry, no, that's the 1296 one. Sorry, I must have. Here is the Audacity version.
Okay.
The reason I put the 1296 one is to show you
Yep.
an example of what it looks like on 1296.
Yes. Okay. Okay.
And you can see that it's the same mechanism.
Yeah, that's right. Similar.
But that was 9 dB.
That was a 9 dB one
Wow.
at 1296.
Okay.
Yeah. Now,
It's a rock crushing signal.
obviously, these were 4 dB and 3 dB, I think. But,
Okay.
but you can still see them there. So I was able to confirm from them that this was lightning scatter.
Okay.
And I know I wrote up the articles for both DUBUS and copied the same one into AR. And then I started, well, I talked to you about, do you want to talk about what we'd put into DUBUS? And I started looking into what else I could learn.
Always good.
Using CoPilot.
Oh, Rex has entered the AI world.
And
Be afraid. Be very afraid.
Microsoft AI World.
Yes.
And I am amazed what
It
can-
knows.
It knows.
Mhm.
And as long as you're very critical and you've got some other evidence to support it,
Excellent approach, Rex.
Yeah.
Excellent approach.
I think it's pretty good.
Yep.
So now, at the time, there were lightning strikes in the middle of the path,
Yep.
which
Yeah, good.
shows you what they were getting them on. It's a shorter path, only just over 300 kilometres.
Okay. Okay.
Compared to the sort of 500
Mm.
kilometres that we've been doing on 1296. Now, this is the lightning map for Australia, and you can see the Brisbane region is much more probable than Tasmania, where we've been doing it.
We're near the station between Broome and Darwin.
Yes. Yes. Trouble is,
Yeah, no. I understand the problems there.
but Brisbane's probably about the best place to do it.
Yeah. Okay.
Now, what started to worry me, I thought, I wanted to learn whether there was an upper limit to the frequency and a lower limit, because when I had done the tests, I'd done parallel test on 2 metres, and I did not get a single ping on 2 metres
I remember that presentation.
at the same time as I got them on 1296. I did get pings at other times, but one of the problems on a 560 kilometre path, or 500 kilometre path on 2 metres, is you still get meteors as well. And so I don't think I got any lightning scatter on.
So they were meteor pings. You.
Well, I can't say whether they're meeting pings because they look very much like lightning pings. But the fact that I didn't get any that occurred at the same time as what must have been lightning pings suggested 2 metres wasn't working.
Yep.
Against that, I've talked to a number of people, and Glenn VK1XX reckons he has seen lightning pings on 2 metres when he's been just working guys in Sydney.
Yep.
And I'm just from Canberra, so just under 200 or 300 kilometres. And they've been doing it on voice. So if you can detect on voice an enhancement, it's got to be a pretty strong signal.
So that's peaks in voice, like you hear the voice go a increase in amplitude. Or
Yes.
something. Okay, right.
And then Brody, as 3MAP's been working, forgotten his name, in Burnie.
Okay.
And they've noticed on 2 metres
That you get enhancement.
you do get little enhancements when there are lightning in Bass Strait.
Okay.
So
They're in the right place because there's lots of lightning up there.
now it's hard to explain why 2 metres would, in some situations, seems to be quite strong lightning pings. But obviously, I mean, there's inverse to the 4th power with distance, so it's going to be weaker. But if it was strong enough on 2 metres that you could hear something,
Yes.
it's a bit hard to explain why we never saw them
On 2 metres.
on 2 metres. So I started looking at what might be the reasons.
Okay.
Now I asked CoPilot about the size of the ionised streamer,
Yep.
and CoPilot told me that that most lightning pings, 80% of them are cloud to cloud, only 20% are cloud to ground.
Okay.
And for cloud to cloud's got the advantage that you're not restricted in terms of the horizon.
Yes.
Now, that could be one reason why I do have a reasonable takeoff to Victoria, but I've got Mount Lofty in the way,
Yeah.
which obstructs to about 1 degree. So one reason might be that there is a difference between cloud to ground, which CoPilot says the ionisation is more intense on cloud to ground.
That's right. Yep.
And so maybe on shorter distances they work on 2 metres. That's one explanation.
Yep.
And
Just keep going.
right.
I'm just going to go and grab a power supply.
All right. We're running short of battery. Okay. In terms of ground, cloud to cloud, the radius of the ionised stream is maximises around 3.5 centimetres. Now, 3.5 centimetres is very short in terms of a wavelength, even at 1296.
Yep.
So I then looked at scattering regions, and the MiE Scattering has a nice peak at about 0.18 of a wavelength,
Yes.
which turns out to be 3.5 centimetres at
Yep.
1296.
Yeah.
These diagrams, they look lovely, but they're a bit hard to understand because they are divided by the area, and if the area is greater, that whole curve would be shifted upwards.
That's right.
So a thicker lightning stream would be stronger, but the peak would still be at the right, at a different ratio, because if it's thicker, it's got a different radius. But
That's right.
But it turns out 1296 looks pretty good. And then,
Yes, it depends on the geometry, and usually the MiE scattering approximations, you assume something about the shape of the scatterer. In this case here, plasma streams can approximate a cylinder, that kind of thing.
right,
And there are some subtle
yeah,
changes, but yeah, you're on the right track, I think, with the MiE scattering.
yeah. Now, you mentioned a cylinder, which shows you that a long cylinder will produce multiple scattering with very narrow beam width,
Yes,
but high gain.
yes.
And once you move into the MiE scattering region, you start to get forward scatter gain,
Yeah.
and once you go beyond the MiE scattering, you move into what they call optical scattering, which really means you can treat the waves as geometrically,
Yes.
and you get very high gains.
Yeah.
And now this is where
This is like aircraft scatter.
it's exactly right,
Yeah.
and that's why aircraft scatter has
Such high gain.
such a high gains.
It's more in the optical region.
Yeah, right. And you can typically get 20 dB gain. Now, once you go up to, say, 10 gigs, you can get much more gain, because the gain goes up at the square of the wavelength, but the beam width gets narrow, and it never gets down to the ground with Earth curvature.
Yeah, okay.
So you actually, but at the higher frequencies, you actually have, because of interference, you get other lobes, and those lobes actually can be at the right angle to get round the curvature of the Earth.
Okay.
And even though those lobes are weaker, your main lobe is much, much stronger, and so you're actually not much worse off.
Yeah.
The only problem is your lobe is now very narrow, and so the amount of time you've got to do any integration is shorter. But I've done a fair bit of work with 10 gig aircraft scatter,
Okay.
particularly with Q65, and it works really well, and it's clearly working on one of these minor lobes.
How many grid squares have you got these days?
Still only 82 with David 38Z.
Yeah.
Yeah.
But that's the highest in Australia. Is it still the highest in the world?
Oh, number of grid squares? I suspect so, but I don't have any. Oh, yeah. Oh, absolutely. Yeah.
10 gigs. Well, it's right.
Yes. Yes.
Yeah, yeah. Okay. Hang on.
So
All right.
now, I then took this classic MiE scattering diagram and and extrapolated. By the time you get to 2 meters, you're way off the bottom of the graph, and this slope is inverse to the fourth power.
Yep.
Now it turns out that 1296 and 3.5 centimeters is right on the peak. 2.4 is only 1.9 centimeters, but because it's a different ratio of frequencies, the peak actually would be on a thinner ionisation channel.
Yep.
And the advantage of that, which CoPilot explained to me, is as you go up in frequency, you need a higher density of ionisation. And so when the lightning actually flashes, there's a core that's only half to 1 centimetre in diameter, of very intense ionisation, and then that expands.
Yep.
So you can sort of see why 2.4 will work pretty well, but will be a slightly different situation when the core diameter is smaller.
Okay.
432 should work. It's going to be about 16 dB less than 1296.
Okay.
And there are references where hams have, well, there's only 2 hams done lightning scatter, and they didn't do it with communication. They just
It
looked
was
at it.
television, wasn't it?
One was television at about 800 megs, and another one was a 432 meg beacon.
Okay.
So we know 432 works, but again, you'd be very surprised that 2 meters works at all, unless there's a different mechanism.
Okay.
Yeah, well, it's the geometry of the situation that allows other things to, kind of move around in that space favourably.
So then I asked CoPilot about how it thought the lightning scatter would work with frequency.
Right.
Okay.
And it concluded that 2.8 gigs would be the top frequency which used the central core.
Okay. Okay.
And only sort of 1 to 3 centimetres, which sort of is in line with the MiE peak for 2.4.
Okay.
MiE peak, is it, or MiE
Yes,
peak?
MiE. Well, I say me, you say MiE.
Okay. Well, I must admit, I used
MiE
to...
Scattering is actually probably the correct pronunciation.
It's
Right.
MIE, isn't it?
Yes.
It's MIE. Yeah.
It's
Named
a
after the
French.
Yeah.
Yeah. French or German?
MiE,
Yeah.
French, German.
Anyway, this nicely suggests that for 2.8 to work, it's very near the limit.
Yeah.
Right.
And it's for 2 meters, which is down in this 90 to you can make it work with much less electron density. I mean, this is 10 to the 11th, so it's 100 ratio of 100 less electron density.
Yep.
So you've got time for
So that's
for it to expand. The probability of, according to radiuses of 7 to 10 is much lower,
Yeah.
but it does suggest it's possible.
So, would you be able to measure that difference between the higher frequency off the core and the lower frequency, like 2 meters off the outside? There would be a delay there, wouldn't there?
It's not very long.
No.
Like it's small.
The whole thing happens in about 50 microseconds.
Yeah. Okay.
But what you might be able to do is with VLF measurements, you can actually work out the current in the channel by measuring the VLF spectrum
Okay.
of the event. And so it'd be interesting to try that, and it might help, correlate with the, particular peak signal strength potentially. It might tell you something, if you've got a really strong current, you'd have a lot, you'd have maybe a larger channel, and maybe you might see things shift in frequency, the peak of it.
So do they have classifications of lightning events? Like
yes.
yeah, okay.
Yes, there's a
Okay.
whole zoo of these things, and
Okay.
the Q bursts are the ones that are the most intense lightning events.
Okay.
And you see these at ELF frequencies, and you can see them worldwide, basically.
Yep.
So there's some data that we could apply if folks are measuring the scatter events, we can measure things at VLF, and you can see them. You don't have to be right at the site, you can be a long way away. And of course, the other thing you can do is you can track down with the various networks, the Worldwide Lightning Location Network, one in particular. You could narrow down where the lightning strike was by time of flight, probably to within a couple of kilometres.
Okay.
So if we knew the time precisely, we could tell you exactly where the lightning event was.
Which we get from...
And we could tell if it was cloud to ground or cloud to cloud.
Okay.
How can we tell that?
We can do that two ways. Basically, again, the spectrum of the VLF or ELF
I see.
spectrum will tell you something about that. And that's what they apply in these networks to distinguish between cloud to cloud and cloud to ground. So there's a number of things that can be added on. Yeah, it's fascinating.
Okay.
I like your comment. There's a whole zoo of it.
Yeah, that's nice. Yeah.
So,
A lot of interesting stuff.
based on my consultation with CoPilot, my concluding remarks are upper frequency limit of 2,800 megs, and he explains, or CoPilot explains, this is at this sort of height, the ionisation forms is offset by decay at the same rate, so you never get the ionisation is saturated.
Yes, that's right.
And therefore about 2.8 gigs is the limit.
Okay.
And at least we've got now some results at 2.4 gigs.
Yes.
The lower scattering frequencies drop off with Rayleigh scattering, which is substantial. 1296 is about optimum, but 2.4 gigs is obviously possible. 144 reported over shorter distances, and it just seems like it's a different mechanism to 1296. I mean, it's associated with lightning, according
But it's
to
a different part of the lightning.
possibly it's cloud to ground, which are more intense.
Okay.
But the probabilities of a very wide radius, which you'd need for 144, don't increase that much with cloud to ground. So what we really need is a lot more testing, perhaps over shorter distances, where we know that they really are 144 megs ones and 1296 meg ones at the same time, to try and disentangle this. And unfortunately, lightning scatter doesn't happen very often down here in Tasmania. But
Well, in southern Tasmania, no.
no. So,
Northern
northern appears to be more, but that's optimum for us because we need it halfway between Hobart and the mainland, where I've got Brodie. And perhaps I really need to add 432 in as well, but I don't have enough equipment to sort of run three bands in parallel
That's right.
at the same time. So I think it's opening up some interesting stuff, and bearing in mind that at this stage, when I published the article on the first lightning scatter QSO in DUBUS over 12 months ago, I specifically asked if anybody had completed the QSO.
Experience. Yeah.
And nobody's ever mentioned it, so I think this is something we're doing in Tasmania that's
unique. That's well and truly. And DUBUS goes worldwide, so you're getting it to the enthusiasts in microwave bands that are the experimenters. So, well and truly.
Yeah. I mean, in part, you've got to be aware that the lightning's available, which you can download a lightning app and it'll tell you, and you've got to both be ready to go.
And preferably on multiple frequencies is what I'm hearing.
Yes.
So you can do that correlation.
So that's where I actually think we might finish there, because the other paper that we've got in on
optical stuff.
on our optical stuff,
Yep.
probably deserves
A separate one.
a separate one.
So, can I suggest the 13th of August, and that's an excellent segue, Rex. So thank you for your talk, and the input. Thank you, Andrew. We have done a little bit of rearrangement with our presentation and events scheduling, because some of our presenters are not available on the days that we originally thought they were available. So we've done some changes. Those changes are the very first. So next Wednesday night was going to be, it's our first Wednesday night of August, was going to be our presentation night. The presentation night's now been moved to the 20th. And so next week is what we're doing is putting on our forum night, which is your favourite digital mode. So, and anything from CW to lightning scatter using WSJT.
Yes. I've got too many favourites to have a single favourite.
Okay. Well, there's your challenge, Rex. There's your challenge.
I think it'll be FST4
Oh, okay. Righto.
for optical.
We look forward to hearing about that next week. So that's next week. We then have and that can be the 13th.
Yeah.
So the
and
next.
if Andrew's available, that would be good.
Yeah. So that's we've got two focuses on that, which is one which is amateur radio focused, and the other one which is focused very much on something very dear to all of us, which is blood. So there is we've got a little segment around, because there are quite a few of us who give blood. So we're doing a bit of a promotion around blood donation.
And that's on the 13th.
That's on the 13th. Yes. Yeah. So that's okay.
Yep.
And then on the 20th we've got our presentation by Andrew Johns about his father's diary.
Yeah.
And then we've got another DATV night. So we've sent out some correspondence around this to try and get people, because we realise that the change begins next week. So we've got a range of things going out around communication around that. So our next presentation, we'll lock that in for the 13th.
Right.
So fantastic. And that is an excellent place to stop. So the other thing was, we usually do a space weather, a bit of a summary of space weather. Can I just say there hasn't been anything of note just in the last week, and I've certainly been watching. So there is no use doing a space weather report, and we've done our future events. So thank you, Andrew.
Thanks.
And thank you, Rex. That's been fantastic, and we've got some fantastic comments on here too. We've got ZL4ES. So we do have somebody from New Zealand on. We've got Ken on, but he's in Albury.
Australia.
In Australia, because they Margaret and Ken would have gone to the Alara 50th anniversary in Melbourne last weekend.
Oh, okay.
Like Linda and Martin. And a bit of a shout out to Linda as well. Bit of a shout out to Linda. Linda's had has a brand spanking new hip. So, and I understand that happened not that long ago. So yes, that's a bit of a shout out to Linda in hospital. So that's your, in the words of a famous Tasmania, that's your blooming lot for this week. And this has been VK7 OTC, the club station of the Radio and Electronics Association of Southern Tasmania, with our DATV Experimenters Night and 73. Have a good week, and we'll see you at the forum and online next Wednesday night. So cheers.